Hi, everyone. It is my pleasure to introduce Ben Weintraub from AWS's strategic partner, New Relic. I have had the privilege to work with Ben and his New Relic team on their journey to Amazon managed streaming for Apache Kafka, a journey he will share with you over the next 30 minutes. Take it away, Ben.
Hi, everyone. Like Colin said, I'm Ben Weintraub, and I'm an engineer on the Kafka platform team at New Relic. The Kafka platform team at New Relic manages about 20 multi-tenant Kafka clusters with a combined ingress throughput of almost 40 gigabytes per second. And I'm going to talk today about how we approached a major transition from a single large cluster running on hundreds of bare metal servers to a set of smaller clusters running in Amazon MSK. We're going to do the agenda today in 4 parts. The first section will be talking about the usage of Kafka at New Relic before we began this transition. In the next section, we'll give a little context about our cloud migration and our move to cellular architecture. Next, we'll talk about obstacles, challenges, and lessons that we learned about our move into the cloud and into MSK. And finally, we'll discuss some of the results from this transition and talk about what's next for us. So let's start with the Kafka landscape at New Relic and what it looked like before we began our transition. New Relic is a full-stack observability platform that allows our customers to monitor, analyze, and optimize their entire software stack. So in order to do this, we need to accept a lot of data from a wide array of sources. That's the stuff you see on the far left of this diagram along the y-axis. This includes everything from instrumentation libraries embedded within customer applications, to mobile devices, to JavaScript code running in some browser somewhere. Almost all of these interactions, though, come down to an HTTP request. When receiving incoming data over HTTP, our first goal is to get it out of a socket buffer and onto durable storage as quickly and reliably as possible. Kafka is a great fit for this, since it transparently handles both disk persistence and replication across multiple machines. Once we've got the raw data written into Kafka, we then feed it through a pipeline composed of various services that aggregate, normalize, decorate, or otherwise transform it before writing it into some persistent database. It's hard to show on this diagram, but a given piece of data might transit back and forth from a Kafka topic to a service 3 to 5 times in our system before reaching its final destination. Most of the data that flows through our Kafka cluster eventually finds its way into NRDB, which is our custom telemetry database, which is then queried from all of our UIs and customer-facing APIs. NRDB ingests over 1 billion data points per minute, and if you take that and consider the previous statement that each piece of data makes multiple hops back and forth to Kafka along the way to its final destination, it becomes clear that we need to support a high volume of data flowing through Kafka. Before we started our transition in late 2019, here's what our Kafka cluster looked like at New Relic. Notice first that I said cluster rather than clusters because we had one big cluster comprised of about 300 brokers running on bare metal. Those 300 brokers were doing a combined total of about 20 gigabytes per second of Kafka ingress, and that's not counting replication traffic. We had a replication factor of 3. We have about 400 topics and 16,000 partitions at that time, and we had mostly short retention windows in the range of 30 to 60 minutes for most topics. The image in the background here is a visualization of this cluster, with each node representing a broker and the lines between them representing replication traffic flowing between brokers. The one giant cluster pattern is one that we found ourselves falling into not just for Kafka, but for other systems at New Relic as well, including our NRDB cluster. It's nice in that it keeps maintenance and operational overhead low, but it also has a number of problems. The most obvious is that a perturbation anywhere in the system can lead to a global outage. Since we have a multi-tenant system, this could be something like a single customer suddenly sending us a huge amount more data, or a human accidentally running a command that applies to too many machines, or an upgrade of a critical service that falls over under load. The next problem is that we knew that our Kafka and NRDB clusters couldn't continue to scale indefinitely, but we didn't know which dimension of scaling would become the bottleneck first, or at exactly what point. sometimes the answer to these questions isn't clear until you are already too far down the road and you've already started to see performance or reliability problems as a result. So we knew there was this lurking scalability inflection point out there, but we didn't know where exactly, and our environment was so large that it wasn't feasible to duplicate it in order to run a test and find out. Lastly, and most importantly, we found out that having a single large production environment was starting to slow us down in all kinds of ways. It was slowing down our ability to make major architectural changes to key systems, slowing down our ability to upgrade key components like Kafka, and slowing down the process for teams wanting to deliver new functionality for our customers. The point about fault tolerance became painfully clear to us during an incident in 2018, in which a single change to how our NRDB cluster interacted with Zookeeper resulted in a multi-hour outage across multiple products and services. This incident thankfully didn't directly involve Kafka, and we didn't lose any of our incoming data, but afterwards we realized that there was fundamentally nothing preventing a similar problem from impacting our shared Kafka cluster. Having only a single environment with a realistic load profile meant that we didn't have a good way of evaluating changes like this without potentially destroying our entire production environment and impacting 100% of our customers. Aside from the fact that we had one giant cluster, we also were running it all on bare metal. The complications of owning servers are probably not new to most folks watching this, but a short anecdote to demonstrate. So Kafka is in the business of writing data to disk, and as a result, we traditionally ran our Kafka brokers with fancy RAID arrays of SSDs. Here's a picture of a rack with a bunch of those arrays from one of our data centers. And this chart gives you a sense of the level of minute detail that we had to get into to monitor all of those disks. SSDs have a finite number of writes that they support over their lifetime, a concept known as write endurance. And in order to avoid performance problems that arise when you try to write to a worn SSD, we have to monitor not just every host, but every disk attached to every host. This chart shows the remaining write endurance for the disks in a subset of our Kafka brokers over the course of the last 6 months or so, pulled out of NRDB via a query. Every one of those circles at the bottom of the chart where a series peters out represents a case where a disk reached its alerting threshold for write endurance, and an engineer from our team had to run a script to cause an LED on that SSD to blink so that another New Relic engineer in our data center could go and pull the drive to replace it. This is a huge amount of work for everybody involved and not really work that we wanted to be in the business of. So let's talk next about our cloud migration and our move to cellular architecture. The key thing that we realized from a business point of view was that delivering new capabilities on the existing stack had become too risky and too slow. SaaS companies that don't continually improve and deliver new capabilities don't stay in business for very long. So for us, this represented an existential problem. We also realized we didn't really want to just lift and shift our existing design to AWS. The problem wasn't just the ownership of the hardware, but also the scale of the environment, like we talked about. So let's look at a simplified version of that first diagram so that we can dig into how we re-architected our systems in order to solve these problems. Starting from the left on this diagram, we receive HTTP requests from a wide array of sources that supply incoming telemetry data from our customers. Those HTTP requests get handled by our ingest tier and written to Kafka topics in the giant Kafka cluster discussed previously. From there, the data gets transformed and aggregated in various ways by a collection of services labeled on this diagram as pipeline services. Most data in our system then finds its way into the insert worker tier, which is responsible for aggregating it and inserting it into NRDB. And finally, our customer-facing UIs and APIs query NRDB. Thinking about how we wanted to change this system for the better, it's worthwhile remembering what our goals were. Firstly, we wanted to limit the blast radius of incidents like that one from 2018 that we talked about. We also wanted to lower the risk of experimentation with new techniques and new versions. We wanted to enable larger overall scale so that we could accept more telemetry data from our customers. And we wanted to enable failover of data ingest in the event of an emergency between different environments. A reality in the monitoring space is that our workloads tend to be dramatically more write-heavy than read-heavy. So figuring out how to do the writes in a distributed fashion was the most important problem to solve, which meant moving the data first. And specifically, we needed to figure out how to not just move it, but partition it in such a way that we could have isolated deployment environments. And we needed to figure out how to do this incrementally. This was such a large change to our architecture that there was no way we were going to be able to make a hard cutover. We needed to design our system to facilitate a transition that we could do gradually. This is a scaled down version of that diagram we were just looking at that we're going to build on to explain how we did this. So within our data center, we've got our ingest services writing to Kafka and then eventually flowing into NRDB after being transformed. And we have what's labeled presentation layer here, which is a placeholder for lots of user-facing UIs and APIs. The first thing that we did as part of our transition into the cloud was to interpose a routing layer between traffic flowing into our data center and our customers, which allowed us to solve the problem of how to incrementally transition traffic from one location to another. We solved this outside the Kafka layer at the HTTP layer. We next created a bunch of scaled down versions of the data ingest and storage portions of what we had in our data center in AWS. These are all isolated environments, even down to being isolated in separate AWS accounts. Now that we are going from having one giant Kafka cluster to manage to having n Kafka clusters to manage, we felt it was important to keep the overhead of that cluster management lower. And so we did that by utilizing Amazon's Managed Streaming for Kafka, or MSK, which is the purple box in each of these cells. Having all the data is great, but if it's spread out across a bunch of places, you also need to be able to query. So our NRDB team built a component called the query router, which was able to take an incoming query and transparently fan it out to the right set of environments in order to fetch the data needed to service that query, possibly including our continuing to exist cluster in the data center and one or more cells. Lastly, some kinds of workloads that we have involve aggregating data that might reside in different cells. So to facilitate that during the transition period, we used Kafka MirrorMaker. We used Kafka MirrorMaker instances to mirror a small subset of the data from each cell back into our old data center-based Kafka cluster for aggregation purposes. To give you a sense of where we are along this path right now, the purple line here represents the combined Kafka ingress throughput for all of our cells running on MSK. And the green line represents throughput to our existing giant cluster in our data center over about a 5-month window. You can see that those lines have crossed and that we're now handling significantly more data in MSK than we were in the data center at its peak. So let's talk next about the things we needed to change about how we operated Kafka in order to operate more effectively in this new environment. We realized that we had gone from a place where we owned a single Kafka cluster to order n Kafka clusters, where n roughly correlates to the amount of data that we receive from our customers. So figuring out how to better automate our story for operations and monitoring became critical. The first challenge was that all of our existing observability tools that we relied upon were suddenly gone. As engineers working at New Relic, we use our own product, and the parts of our product that we relied upon to monitor Kafka relied heavily on the ability to collect data from software that's running directly on the Kafka brokers themselves. That's no longer an option with MSK because we don't have direct access to the brokers. The MSK team also recognized this lack of observability as a serious issue and has made some great improvements in this area over the past year or so. After several rounds of iteration, the solution that we landed on for this problem was to make heavy use of the open monitoring with Prometheus feature of MSK. This is an optional feature that you can turn on for MSK clusters, and it exposes all broker metrics that are collected by Kafka, rather than just a select subset. And it also allows you control over where you send the data to, the shape of the data, any transformation or decoration that you want to do on it, the sampling interval at which you harvest that data, and the retention, how long you want to keep it for. So it offers us a lot of flexibility. The system that we built in order to use this feature consists of a small service that we built using the New Relic telemetry SDK that harvests from the Prometheus endpoints exposed by all the brokers running in each of our clusters, does some amount of aggregation, decoration, and transformation, and then uses the New Relic telemetry SDK to easily send that data into NRDB. Once it's in NRDB, we have a unified interface that we can work with it all from, using it to drive dashboards, NRCL alerts. NRCL is our New Relic query language, ad hoc queries that we use for debugging and automation. To give you a sense of how we use that data, here's a screenshot of a New Relic dashboard that gets provisioned automatically via our dashboard API for every MSK cluster that we create, which displays the data that we were talking about harvesting on the last slide. We also have a dashboard that shows how all of our cells are doing relative to each other, so that we can get a sense of the workload distribution across all of these different environments. The next challenge we ran into was a change in the way that we needed to think about broker performance and scaling. In our Kafka use case, we're primarily write-bound. Every write into Kafka originates with a producer, gets sent over the network to a lead broker, gets written to disk on that broker, and then gets sent over the network again to one or more follower brokers. In our data centers, we ran brokers with fancy RAID arrays that could achieve high write throughput on the order of 2,000 megabytes per second. This meant that we were used to the network, which topped out at 10 gigabits per second, or 1,250 megabytes per second, being the bottleneck, and we could mostly ignore disk performance. With MSK, you switch to using network-attached storage via EBS GP2 volumes. These are SSD-based volumes that offer good latency, but a much lower level of storage throughput than we were accustomed to, only about 250 megabytes per second. This is a trade-off. On the plus side, because these are network-attached volumes, broker restarts become very quick. MSK doesn't need to rely on Kafka replication to move state over, and they just reattach the same volume to another EC2 instance. But also it changed where the bottleneck in our system was. We now have to pay a lot more attention in terms of alerting and monitoring to disk throughput than to network throughput. When we highlighted the importance of monitoring disk throughput to the MSK team, they were able to quickly expose metrics around disk throughput via the MSK open monitoring feature that we talked about earlier that helped us solve this observability challenge. Another important thing that we realized as part of this transition was that while MSK lets you select your instance type, CPU and RAM scale with the instance type that you select, but your disk throughput does not. For us, this placed an upper bound on the largest instance type that made sense for us economically to use with MSK. The final set of challenges that we faced was around learning about some new failure modes and how to mitigate them. There's two that I want to talk about, but before we get into them, let's do a brief review of how Kafka failovers work. Kafka is a replicated system, and to some extent, it can handle the death of individual Kafka brokers gracefully. The way that traditionally works is that you've got a client talking to some lead broker. The lead broker is replicating to a follower, and then each broker within a Kafka cluster is also sending periodic heartbeat messages to Zookeeper in order to keep a Zookeeper ephemeral Z node alive and indicate that it's still able to accept traffic. When one of your brokers has a problem, say it loses network connectivity, those links to both the client and to follower brokers and to Zookeeper are all severed. The ephemeral Z node disappears from Zookeeper, and Kafka initiates a failover, electing one of the brokers that was previously a follower to take over leadership, and redirecting clients to communicate with the newly elected leader. So, MSK stores the Kafka log directory on an EBS volume. which means that your disk is now also across a network. It's a different kind of network, but a network nonetheless. And the salient fact about networks is that they fail sometimes. So this opens up a new failure mode when the connection between one of your brokers and the disk that it needs to write to becomes degraded or fails. In that scenario, the producer that's trying to write into the broker will see problems because the broker will begin backpressuring requests because it can't write to its disk, at least not fast enough to keep up with the writes from producers. The Z node, though, in Zookeeper will continue to stay alive because the broker will continue to be able to send heartbeat requests to Zookeeper successfully. Its primary network interface is working fine. The second failure mode that was new to us involves the fact that in MSK, the notion of the network connection is not monolithic for brokers. In our data center, we've traditionally run replication traffic and client traffic through the same network interface. And currently in MSK, that's not the case. Replication traffic and client traffic are serviced via different ENIs on the broker, represented by the green and purple lines on this diagram. This means that you can have a failure of one part of your network without affecting the other. Specifically, the scenario we've encountered with MSK a few times is that the client ENI fails without the replication and Zookeeper ENIs failing. What this means is that you have a broker that's still considered to be live by the cluster, but is not reachable by clients. The lesson here is that Kafka failover alone won't save you. So what can you do? Well, since Kafka reliability is so core to everything we do, this is an area where we've pushed the MSK team, and they've been working hard on improving their offering. The direction that they're currently pursuing is building an external customer canary feature that injects synthetic traffic into the Kafka cluster in order to provide more active failure detection and eventually transparent remediation of issues like this much more quickly. Until that arrives, they've also delivered a stopgap measure, which is a safe broker restart API that you can use to force a broker failover. Another option, which requires you to build a bit more tooling on your own, is that you can reassign explicitly to in-sync followers of the broker that's having a problem, effectively relieving it of leadership duties very quickly, assuming that you can automate the generation and application of those reassignments. So let's wrap up by talking about some of the results from our transition and also some of the unsolved problems that we still need to address. This is one of my favorite charts from my time at New Relic. It shows about the last year's worth of data volume flowing into our NRDB cluster, broken out by environment. The mustard color that you see on the left is data flowing into our NRDB cluster in our primary data center. And the rainbow of other smaller bands is showing data flowing into NRDB in all of the cells that we talked about earlier. You can see that for a long time, this was a pilot project and we had just 2 cells that were live. And then around April of 2020, we started to redirect a lot of traffic into those cells and draw down the amount of traffic in our data center. This has allowed us to shrink the footprint of our data center, although there's still a significant amount of traffic there. Not using MSK for this migration would have likely pushed out the timeline significantly as we built out the tooling necessary to run Kafka in a cloud-friendly way. In terms of operational results, which is the thing that my team cares about the most directly because it impacts our daily lives, I want to highlight 3 major wins. One is that having smaller clusters with MSK has enabled us to do the first 2 major version upgrades of Kafka in years at New Relic. We've been stuck in our data center on Kafka 0.10.2 for quite a long time, and part of the reason we've had trouble moving past that is this fear of breaking our entire production environment. MSK handles the entire process of doing rolling upgrades for you, and these upgrades have been almost entirely painless. We also have achieved 2x better resource utilization, which really comes down to how difficult it is to plan for and provision new hardware in our data center versus how easy it is to do the same in AWS. Lastly, there's a bunch of code that my team needs to maintain for facilitating rolling deploys of Kafka brokers. At the moment, we still have to maintain that code because our data center cluster remains live, but at some point in the future, we'll be able to get rid of it. which is exciting to us. In terms of business results, a big one is that we're now able to deliver much larger overall scale. We don't have this lurking scalability wall, which means that as a business, New Relic is actively engaged in trying to make sure that we collect as much operational data from our customers as they want to send us. We don't ever want our ability to collect data to be the bottleneck for growing our business. We can also now deliver new features faster and with more confidence. Two recent examples of that are our logging product, which started in our data center, but when it became clear that it would be more popular than we'd be able to support there, we shifted that traffic into our cells, which has been a key enabling factor for that product. More recently, our remote write support for Prometheus, where our customers can configure their Prometheus data to flow directly into New Relic dimensional metrics, would have not been possible to build safely within our existing data center cluster. So that traffic went directly into cells. And the fact that we had this better scaling story made it possible for us to deliver that feature. Finally, in terms of remaining work, the biggest piece is that we've now created two different levels of workload balancing that we need to deal with. The first one was one that we are familiar with, which was balancing Kafka workloads among the brokers within a given cluster. But the second one was one that was new to us. The second level of balancing we need to pay attention to now is across our various cells. This visualization is a 2D histogram that's showing the ingress volume of Kafka brokers across our different cells. Each row of the histogram represents one of our cells, and each column represents a level of ingress throughput. The color intensity of each box represents the number of brokers within that cell that fall into that ingress bucket. The pink line is where we'd like all the brokers in all of the cells to be. Ideally, this diagram would be a thin blue line right over top of that pink line. But you can see that we have work to do in terms of figuring out how to best balance our diverse set of workloads across this set of different environments. Given how much engineers enjoy solving interesting algorithmic problems, we're confident that we'll be able to get there, but it'll take some time. Thanks for listening, and thanks for hearing about New Relic's journey into the cloud with our Kafka cluster.